Recording in progress. Good. Okay, I'm going to do some of the stuff in a shared presentation, which you will get, and some of the stuff I am going to write on the board behind. So here we go. Okay, I'm going to share the screen. I hope I'm going to share the screen. So here, this is where we start today. So we are today, come on, wake up. Right, today we are in the Schools of Hope Chemistry Department with Teacher Mark. That's what we're doing today, and today we are going to move on, and we're going to move straight to metals. And in metals there is quite a lot of chemistry, and what I'm going to do is I'm going to introduce all of it to you to start with. I have a picture of an elephant here, not only because I like elephants, but because after this lesson you should be able, like an elephant, to remember everything. And this elephant is made of metal, and it shows two things about metals. One is that they are structurally very strong, and we will talk about metallic bonding and so on. But the second thing you can see is that it is rusting, and this is one of the problems for a metal. Here is the syllabus. There is no point in writing it down. Do not write down the syllabus, but I will tell you what we are going to do. So the first thing we will do is about extracting metals, and you have to know some ores, you have to know the main ways that they are extracted, you have to know how to get sodium, aluminium, iron, copper and zinc from their ores. You also have to know some of the properties, and the properties are simple, lots of chemistry, lots of physics, it's simple stuff. And then you have to know some uses, and then finally some pollution effects. But more important than that, not worth writing, more important than that is this. And I don't want you to write this down. It will be on a list which you will get from your supervisor. But this is what you actually need to know. You have to be able to name some ores. You have to know how to extract metals, the general methods. You have to know specific information about some metals like sodium, like aluminium, and so on. You have to know about the physical and chemical properties of metals, how their alloys and metals are used, and then problems with them. So this is what you need to know, and this is what they ask questions about. That's the most important bit. Today, what we're going to try to do is we're going to do this bit. Okay, this here, and we're going to start with the ores, the metal extraction methods, and then the electrolysis of aluminium and the extraction of iron, and I will let you do some of the other stuff yourself. Okay, we probably won't get to look at the uses of metals and their physical properties, which will be next time. Okay, so here we go. So the big deal about metals is that, firstly, some of the metals have been used for thousands of years. They have found gold and silver, which has been used to make things for thousands and thousands of years. They have used bronze, we have used iron for thousands of years. But some metals are still very difficult to get out of what we call their ores. Don't bother writing anything yet. I'm just trying to introduce you to the ideas. So some of them have been known for years, and some of them are still difficult. How easy it is to get a metal out of its ore depends on its reactivity. Now, so what we need to know is firstly about the reactivity series. And you have probably come across the reactivity series from the most to the least, or the least to the most, it does not matter. You have to know the reactivity series. What I would like you to do now is just to see if you can write down the reactivity series of metals. What is the most reactive metal you know? What is the least reactive? I will give you some names. So we have things like iron and sodium and copper and zinc and aluminium and magnesium, potassium. Which one is the most reactive that you know of? Which is the least reactive? I'll give you a moment just to think about this. So what ones can you think of? So have a think. Where does sodium come? Where does aluminium come? Where does zinc and iron and lead and copper and so on? Nice coat, Kabiro. Nice coat. So come on then. Who has a list of metals in order of reactivity? Who can tell me some of them? If you want to write it down and show me it on the camera, that would be great. I would like to see anybody who has an idea of the reactivity series of the metals. Talk with somebody else. See if you can remember this. This is the sort of chemistry you need to know. Okay, very important. Very important. Potassium is the most reactive. That's very good. Well done. Potassium is the most reactive that we come across. In fact, in many British schools, teachers are not allowed to show experiments with potassium because it is too dangerous. And so they go for sodium. What is the least reactive metal you know? Does anybody know a very unreactive metal? You might have a necklace or an earring or something like that made from a metal, one of these metals, a very unreactive metal. Oh, that's a very good list. Let me have a look. Potassium, sodium, calcium, magnesium, aluminium. Go up a bit. Very good. That's very good. I like that very much. Well done. I like that you include hydrogen. That's really good. Silver Spring. Okay, I'm going to go back and share. I want you to think about these. Silver, very unreactive metal. Very good. Yes. If my voice is very low, I think it is because your speaker is low. We'll just see if we can turn it up a bit. Hang on. Let's just see. Is that any better? Maybe this is better. I hope that's a little bit better. Teacher David, thank you very much. I'm sorry if it is low, but the microphone here says it is quite high now. But anyway, let's go back to the sharing the screen. Okay. Excuse me. Okay, so the reactivity series goes like this. And this is worth writing down. Don't bother with the second column, electrolysis, heating with carbon and so on yet, but do write down these: potassium, sodium, calcium, magnesium, aluminium. It is worth putting carbon in here. It is not a metal, but it behaves importantly with metals. It is used in extraction, so we need to know it's there. Then it goes zinc, iron, and then hydrogen can also go after iron, before copper, and then copper, silver, gold. Okay, that is important. It is important that you have some way of remembering this. So memory is very important in this sort of piece of chemistry. And let me give you a way that I talk about with my students, and we'll see if it makes sense to you. This is a pretty silly way of doing it, but this is what we do. So we either try to remember the formula, the symbols or the names. And if you're remembering the symbols, sometimes the best way to do it is to put them together into words. I'll give you an example. So you can join all the letters together and try saying it, or you can turn it into a sort of sentence. So this is a sentence which one of my students came up with. K, like okay. Nah, meaning no. Come gal, meaning come on girl. Zun for peb, cool. Now that doesn't mean anything, obviously doesn't mean anything, but it's just all the elements, symbols in the right order. And it looks pretty stupid, but if you can get into an examination and write that down, then you know the order of reactivity. There's a different way of doing it. Some people use the first letters of the names. Here's a stupid one that one of my students came up with. It's pretty scary climate makes a zoologist ill like crazy. It's a stupid sentence, but when you look at it, it's the first letters of the names. Potassium, sodium, calcium, magnesium, aluminium, zinc, iron. Do you see? See how it works? It's really important that it works really simply. Lead, copper at the end. Silver and gold and platinum are less reactive than copper, but they hardly ever ask any questions about them. So try to come up with your own way of remembering it. Use either the symbols or the names, don't use the two together, and see if you can come up with your own way of remembering it. Pretty scary climate makes a zoologist ill like crazy is pretty stupid. I can see somebody at Silver Spring. Show me that. What have you got? Oh yeah, okay, good, okay. I will stop calling you a zebra, of course. Here we have, please stop calling me a zebra. Instead, what do you say? Try learning how. Oh, yes, good, very good. It doesn't matter how you remember it. It's very good. Well done. Whatever way you remember it, try to remember it. Now, going back to the previous slide, the important thing here is that all of the metals above carbon have to be got out of their ores by electrolysis. All of those below, at least down to copper, silver and gold, are heated with carbon, and the carbon is more reactive, so it will take the oxygen or whatever away from it. Okay, so that's quite important. So potassium, sodium, calcium, magnesium, aluminium, all electrolysis, all the same method. Zinc, iron, copper, all heating with carbon. Copper sometimes is mainly pure. Silver and gold, basically you just have to melt them out. Okay, I'm going to stop share just for a minute. So far, 1, we need to remember the reactivity series. 2, the reason we have to remember it is because this tells us the general method for extracting the metals. Okay, I hope, Teacher David, you can hear me okay now. So I'm going back to share and on we go. So here we are. Silly ways of remembering, doesn't matter. And here are 3 ores, pictures of ores: aluminium oxide, iron oxide, and copper. In various forms, it's copper carbonate and hydroxide. You have to know what an ore is. An ore is a metal or metal compound that is concentrated enough to make it worth spending the money trying to get the metal out. You see, almost all rocks contain many metals, but most of the time it would be too expensive to get them out. Some unreactive metals like gold exist pure. Now the aluminium oxide is a bit strange here. The aluminium oxide on the left top is brown, and this tells us something. Aluminium oxide is actually white. So this tells us that aluminium oxide contains, or bauxite contains, aluminium oxide and something else, and the something else is iron oxide. Now, this is something that you need to know, but I'm going to simplify it, so don't write this down. Do not write. This is a list of many ores, their names, some of their formulas and so on, but I'm going to simplify it for you because they hardly ever ask more than 1 or 2 simple questions. So these are the ones which are worth knowing. These are ones that they might ask about. Now, some of them you know, so some of them there is hardly any point in writing anything because you know probably that sodium comes from salt. But the ones that they ask about a lot are aluminium, zinc, iron and copper. Okay, they are the most common ones that they ask about. So if you do not already know this, write down the metal with the name of their ore and their formula. That would be worth doing, okay? If somebody wants to write it down and send it to everybody else, that is okay. But I would write down the metals, the name of the ore, and their formula just now, because this is something you need to remember for the examination. Sodium is in sodium chloride, NaCl, no problem. Aluminium is called bauxite. Aluminium ore is called bauxite. There is some in Kenya. There is a lot in Russia. There is a lot in Canada. Its formula is Al2O3 for the aluminium, but it also contains Fe2O3. Zinc is called zinc blende. It's also called calamine. You may know of kaolin and calamine, which are both used by doctors and nurses. Kaolin for settling bad stomach, calamine for burns and so on. A zinc blend is ZnS, that's zinc sulfide. Iron is in hematite. Some people spell hematite with an A as well as the E. That's okay. Hematite is okay spelled like this. That is Fe2O3. Lead's main ore is called galena, and it's lead sulfide. Copper is mainly malachite, which is two chemicals joined together, copper carbonate and copper hydroxide. So there they are. These are the ones which are worth remembering. I have only seen 2 questions that have asked for 2 ores of aluminium, which is why I have said there bauxite and kaolin, and 1 question with zinc. So zinc blend and calamine. That's the only reason I have those there. Be aware, there are many others. Look, there are many, many others. There are more than I have written here, but do not remember these. Remember these. Okay. Now, you need to know that the process of getting a metal out of its ore has a first stage, which is about purification. And when we come to talking about pollution problems, you may find that we have to talk about this quite a bit, so that the purification often causes real problems when we are talking about metal extraction. Okay, it's important to know that the metal extraction creates a lot of problems, really a lot of problems. So there is purification, and then there is the extraction. So you need to know that. You start with the ore, then we get a metal compound, and then we extract the metal. So for instance, bauxite, aluminium ore, we have to get all the iron oxide out of it first. This produces many purification problems. We get sludge formed, which is very bad for the environment, and that produces aluminium oxide, and then the aluminium oxide is electrolyzed because it is high up in the reactivity series. Okay, here are just some pictures just to remind you that although you may see extraction of metals, sometimes people do it in small scale in a city. It is actually huge business, huge business. There is a blast furnace near here where I take some of my students to, and it produces more than 1,000 tons of iron a day, sometimes up to 10,000 tons a day. That is a huge amount. That is enough to make 1,000 cars, for instance. Okay, so it is a very big scale industry. All right. So let's have a look at some of the methods, and then I will go through them in greater detail. So this is one of the methods. This is for making aluminium. Don't write it down, we will look at it. But I want you to use simplified diagrams because this is the way to remember things. So that is for producing aluminium. This one is for producing sodium. It is a different method altogether. This is for purifying copper. Copper, when it is found in the earth, is nearly pure. It is, unless it's in malachite. So it can. Guys, can you?
I'm a physics.
Guys, thank you very much. It's chemistry today, not maths. It is physics on Friday. Okay, Friday is for physics. It is mathematics tomorrow, chemistry today. So we have aluminium there, then we have sodium, then we have copper, and they are all electrolysis. And then finally we have this, which is the picture which we just saw, which is for the less reactive metals. This is a blast furnace for producing iron. Okay, so I'm going to tell you about it in greater detail now. So I'm not going to share my screen. I'm going to write on the board behind me. So I hope I'm going to change the camera because the other one is a little bit better for this board behind me. Okay. Okay, so I'm going to deal with two metals. I'm going to deal with aluminium and I'm going to deal with iron. The important thing to realize is that when you know the reactivity series, the basic system for electrolysis or the basic system for reduction using carbon are the same for all of the metals. So if you know it for aluminium, it is very, very similar to that for potassium and sodium and magnesium. If you know the method for iron, that is very similar to that for zinc or lead, for instance. Very, very similar processes. So I'm going to teach you two, and then we will send you the details of the other ones in a little bit more detail. I'm going to start with the easiest one, which is iron. I'm just going to put this up just a little bit. Okay. I'm going to start with iron because iron is not very reactive. You will know that iron rusts, and it rusts because it is reactive enough. On our planet, one, we have quite a lot of water, and two, we have a lot of oxygen. And iron reacts with oxygen and with water to form rust. So our cars fall to pieces, our bridges fall to pieces, our ships fall to pieces. But it doesn't do it anything like as quickly as if we made it out of sodium or potassium. The less reactive metals are extracted by chemical reduction. What chemical, I hope you can see that, I'll bring that a little bit closer. What is important about chemical reduction is that this means there has to be a reaction and it's reduction. Now, reduction is the removal of oxygen. That's all. In this sense, I'll just turn this light down a little bit. I hope it makes it a bit easier to see. The removal of oxygen is a really simple way of thinking about reduction. There are other ways of thinking about it, like with electrons and so on. But the important thing here is that here it is simply the removal of oxygen. Now, iron ore is hematite, Fe2O3. Okay, Fe2O3. So we need something which is going to take the oxygen away from the iron. And what we do is we use carbon. And if we use carbon, that's pretty good. It works okay, but it's not a very efficient process because iron ore is Fe2O3 and it's mixed with SiO2. Now, SiO2 is sand. And if we make iron from iron oxide, which has sand in it, it makes it very weak. It makes it very brittle. So if I have a bridge, the bridge would break. If I have a ship, the ship could crack if there were big seas. So the blast furnace has to get rid of the silicon dioxide, okay? So what happens is this. Firstly, you have to know that there are 4 things which are put into the blast furnace. That is iron ore, which is Fe2O3. We put in coke, not the fizzy type, which is just carbon. We put in limestone, which is CaCO3, and we put in air. And we put in air, we actually want the oxygen, but to extract the oxygen is too expensive. So we use air, and a lot of nitrogen goes through and doesn't do anything. Okay. Now, a blast furnace is a very tall tower. It is very tall. It is. It depends where you are, but there is one quite close to where I live, where this is 90 meters. Okay, that's really huge, 300 feet tall. And the iron ore goes in the top, and the carbon goes in the top, and the limestone all goes in the top. Okay? The oxygen gets blown in through some tubes which are all the way round the blast furnace. And the oxygen burns the carbon. So the first thing that happens is that the carbon burns in the oxygen, okay? So it catches fire. And this produces a lot of heat. So much heat that down here where it is burning, it is something like 1500 to 1800 degrees Celsius. That is very, very hot. I just need to close a curtain so you don't get so much reflection. Hang on. I hope that is a little bit better, yes. Okay, so the carbon burns and it produces carbon dioxide, and the carbon dioxide does something else, which we'll look at in just a minute. So down at the bottom, it is very, very hot indeed. Up at the top, it is much cooler. Up here, it is like only 300 degrees, much cooler. Okay, so these chemicals all go down. And what happens is this. So the first thing that happens is that the carbon burns to form carbon dioxide and lots of heat, a huge amount of heat. But they make sure they have enough carbon so that the carbon doesn't have quite enough oxygen. And what happens is that the CO2 reacts with more carbon to make carbon monoxide. Now you may know that if you are cooking indoors and you don't have enough oxygen, your stove can produce this. And you may know that carbon monoxide is extremely dangerous. You can't smell it, you can't taste it, but it is toxic. So when they use the blast furnace, they have to be very careful, because the carbon monoxide coming out could kill people. And in fact, a few years ago in South Wales, there was an accident when some people went to clean out the furnace after it had been stopped working for a week, and they died because there was still carbon monoxide in there. The carbon monoxide takes, remember the reactivity series, Iron is below carbon. The carbon takes the oxygen away from the iron. So here's the Fe2O3, and it reacts with CO to form Fe and CO2. This is not balanced. This reaction, this equation is not balanced. There are 3 oxygens here. Each carbon monoxide takes 1 away from here. So we need 3 of these to make 3 carbon dioxides. And because there are 2 ions here, there will be 2 ions there. Fe2O3, 3CO, 2Fe, 3CO2. That is most of how the blast furnace works, but there is one extra bit. They have added the limestone, and what the limestone does is it is decomposed, it breaks down with the heat, and that limestone forms calcium oxide, and the calcium oxide removes the silicon. Now, so the iron falls down to the bottom, and we get a layer at the bottom, Fe, and it gets pulled out of the bottom of the furnace. But the silicon would be there and would make it rubbish. So the limestone, CaCO3, when it gets hot, turns into CaO and CO2. CaO is very reactive. The CaO reacts with the SiO2. So the calcium oxide reacts with the sand to remove it, because otherwise the iron would be no good. So it's quite easy to do this. You just add all these together, so you get Ca, Si, 1, 2, 3, O3. This is called calcium silicate or slag, and it forms here on top, and it gets taken out. It is very strong, but not very useful. We put it under roads and so on. The new highway that went through Nairobi, they will have this underneath it because it is cheap, and then you can tarmac over. It will be very strong. So that's the blast furnace. Okay, 4 things go in: iron ore, limestone, carbon, air. Carbon burns, carbon forms carbon monoxide. Carbon monoxide takes the oxygen, carbon more reactive than iron, takes the oxygen away from the iron, and the silicon dioxide, sand, is removed by the limestone. That's the blast furnace. It's recorded, so if you want to see it again later, you can. But there are many YouTube videos and so on of that. Aluminium, much higher in the reactivity series. Aluminium is higher than carbon, so carbon cannot take the oxygen away from it. If aluminium oxide and carbon are heated together, nothing happens. They get hot, that's it. So we have to use electrolysis. And electrolysis runs like this. Basically, if Al2O3 can dissolve in something, it splits up into its ions. Aluminium 3+ and oxygen 2-. Okay, these are the ions. There are 2 of these and 3 of those. And this is what we want. And what we need to do is to add electrons to the aluminium to get it out. So the aluminium has to have electrons added to it to make it into aluminium. If you remember from back in Form 3 and so on, a positive ion is formed when an atom loses electrons. So if I lose one electron, I become 1 plus. If I lose 2, I become 2 plus. If I want to reverse this, I have to push electrons back to them. So the Al3 plus has to pick up 3 more electrons. So here it is. So how we do it is this. We get a big steel tank. Like this. And this is normally steel because that is strong, but it is lined with carbon. And into the top of this, we put some big carbon blocks. And these carbon blocks are attached to electricity, and these here are positively charged, and the whole of the bucket is negatively charged. Okay? Into here, we put 2 things. So in here, we have the aluminium oxide, and something called cryolite. You need to know about cryolite, about why we use a cryolite. It is very important. We'll come to that in just a moment. Okay, so big bucket, which conducts electricity, charged negative, carbon rods stuck in the top, charged positive. If something is charged positive, it is called an anode. If it is negative, it is called a cathode. We will do this when we do electrolysis more, but if you've written it, if you want to know it now, that's what happens. So into here goes this, and this is at about 900 degrees Celsius. 900 degrees Celsius. Now this is good, because aluminium oxide doesn't melt until about 2,300, 2,500, I can't remember. It's a very high melting temperature. That would be very, very, very expensive. Okay? That would be very expensive. So the cryolite is added to make a mixture which has a lower melting point than pure aluminium oxide, because heat is expensive. Because it is expensive, we want to lower the melting temperature so we don't have to burn so much fuel. So, in here, what happens is this. The aluminium picks up the 3 electrons, turns into aluminium, and this happens, here. And we get a layer of aluminium forming at the bottom. So aluminium forms at the bottom. Now, this is the basic pattern of all electrolysis. So if this was not aluminium oxide, but potassium chloride, or sodium chloride, or magnesium chloride, which are their ores, and what would happen is that the same pattern would happen. But if it was sodium, for instance, sodium is only Na1 plus, so it would only pick up 1 electron to form Na. Okay? It would only need 1 electron. So the aluminium needs 3 because it's 3 plus. At the same time, there is a problem because the oxygen is also produced, and the oxygen sets fire to this carbon. This carbon is quite cheap, but it burns away, which is a problem. But we'll come across that. Okay, so the aluminium, this is the main production for aluminium from aluminium oxide. And the cryolite is there to produce a mixture with a lower temperature. Okay, I'm coming back over here. Change camera. Hello again. Okay, I hope that either was okay because you know it already, or it made enough sense for you to go, okay, yeah, I can learn that. I'm going to go on now, and we're going to just look at something just to see if you have picked up anything much. Okay, so what we're going to do now is we're going to test to see if you have learned anything. Oh yes, oh yes. So for those of you at the back, Shama High School, playing with your phone, for those of you in Kabiro admiring your coat, for those of you in Glory laughing at the guy with the lovely coat, with those, hey, the guys in Shama who are too cool with their New York hat. Let's see if you know anything. Here we go. Are we ready? Let's see. So, which impurity is removed at this stage during aluminium? In the purification stage, iron oxide is removed. We will do lots of questions, proper KCSE questions, but in answer to your question, at the stage during aluminium production, the impurity which is removed is the iron oxide. I mentioned it was aluminium oxide and iron oxide, and we have to get rid of that. Okay, so here are some questions. Ready? Let's have a go at some questions. They're only a few, so it shouldn't take too long, but we'll see. Here we go. Pleasure. Okay, here's a question. Name the ore of sodium, of iron and aluminium. Quite an easy start. So what are the ores of sodium, of iron and aluminium? The names, okay, the names. The names of the ores of sodium, iron and aluminium. Okay. Okay, I can see one from Silver Spring. I can see a Glory there as well. Let's have a look. What does it say? We've got hematite, bauxite, and NaCl sodium. Very good. And Silver Spring, I think I can't see your top one, but it looks okay. Shama, what do we got? Hold it a bit closer, please. Show me a bit more, please. Well done. Really, really good. You guys are very good. Soda ash is also true. Whoever put that in, I think that might have been Genesis. That is also true. But the major one is salt. These are really good, guys. I'm impressed. So let's make the question harder, right? Ready for harder? So the answer is sodium chloride or salt, hematite and bauxite. Here's question 2. Give the formula of the ore of a sodium, of iron, of aluminium. Give the formula of the main compound in the ore of sodium, iron and aluminium. The formula. Like if you think iron oxide is PBS, you are an idiot. But that's okay. Okay. So let's see what people have got. So the ore of sodium, of iron, of aluminium. Very good, Glory. Well done, Glory. We're first in. Whoa, Gloria winning at the moment. I'm really impressed, Glory. That's very good. Silver Spring, you're behind. Come on, guys. Come on, Shama. Come on, Shama. Can't teach you, David. I haven't seen your answers. Silver Spring, very good. Well done. I'm not surprised you got that right. Shama, let's have a look. Really good. Well done. Everybody's really, really good. Oh, I like that, Kabiro. That's very good because it is a hydrated one. That's very good. Okay. So the answer. Oh gosh, I changed from. Oh my gosh. Look, I changed from sodium. My apologize. I changed from sodium to copper. If it was copper, it would have been CuCO3. If it's sodium, it's NaCl, iron Fe2O3, aluminium Al2O3. So let's see if your memory will work now. Put the following metals in order of reactivity. Oh, I meant to say most reactive first. My apologies. Most reactive first, please. Most reactive first. Absolutely right there about it being bauxite, but it's spelt B-A-U-X-I-T-E. B-A-U-X-I-T-E. Okay. So put them in order of reactivity with the most reactive first. I'm sorry, this is an old save. I've changed it round. Go most reactive first. Let's see what we've got. Let's see. Let us see what we have got. So put most reactive first, not least, because my answer has it as most first. Who's got it? Okay, you've got it least to most. That's very good, Shama. Shama are going really well today. Could I just see that again, Shama? Could I just see that again, please? Shama, could I just see it again? Okay. Yes. Okay, very good. Well done. Good. Kabiro, have we got a list? Well done. Very good. Well done. I like the included calcium. Hey, Shama, really good. There are a lot of people here. Very, very good. You guys know this already. I'm very impressed. I really am very impressed. Okay, so the answer to my question, which I wrote out wrong, is this because I put most reactive here. I changed the answer. Okay, number 4. Where does carbon come in the reactivity series below? Where does carbon come? I'll give you a few moments just to think. 5, 4, 3, 5, 4, 3, 2, 1. It goes there. Between aluminium and zinc, as somebody actually wrote down really quickly. Okay, it's very important that you remember where carbon comes. Okay, guys, can we? Florence, I'm sorry, I'm just having to mute you there. Okay, next question. That's very good. It's very important that you remember that, because remember, if you know where carbon is, then you know that the ones potassium, sodium, magnesium, aluminium are all extracted by electrolysis, and below that they are either pure or they are by carbon, heating with carbon. What type of extraction will be used for aluminium and lead? Look at them there. Aluminium and lead. I'll only give you a moment for this. Aluminium should be real easy now. Aluminium and lead. Look at where carbon is. I should think you know this. Aluminium should be, and lead should be, oh, I don't know. I can't remember. Well done. Very good. Kabiro. We've got some genius in Kabiro. It's that coat. It makes him clever. Well done, Shama. Very good. I'm really impressed. That's really good. Silver Spring. Very good. Excellent. And the answer is there. Aluminium is electrolysis and lead is reduction, which means heating with carbon. They are both reduction of a type. Very good. Well done. That is really good in the chat. I think, is that Genesis? I think that's Genesis, which is great. Well done. Aluminium electrolysis and lead reduction. Last couple of questions. Name the raw materials put into the blast furnace for extracting iron. Name the raw materials. Name, not formulas. Name. It's important that you answer the question properly. So it's the name of the chemicals which are put into the blast furnace if we're trying to get out iron. Do you want to show me that, Samuel? Well, that's one of them. I can see one. You said Coke. Is that because you're thirsty? No, perhaps not. It's a crap joke. Sorry, it's a very poor joke. My apologies. I could only see one word, which was Coke. Come on, who's going to get all, however many there are? I think there are more than one. So we've got Coke. Come on, Shama. Coke. Fe2O3 CaCO2. No, not CaCO2. No. Try and remember the names. Try and always give names if it asks for names. Have we got an answer here from Kabiro? Kabiro think they have an answer. They have hematite, coke and limestone. That is correct, but there is something missing. There is a fourth thing which is added. Coke, yes. And hot air. Glory come up first. Well done, Glory. So the chemicals which are there, the four which are into there are hematite, which is the iron ore, the coke, which is the carbon, the limestone, which is used to break down and get rid of the SiO2 to form slag, and hot air. The one that people always forget is the hot air. Last question. In the extraction of aluminium, a chemical is added to the aluminium oxide. What is it called and why is it added? In the extraction of aluminium, what is added and why? Well done, Genesis Joy. That is very good. So what is this chemical and why is it added? That's very good. It's important. That's very good, Kabiro. It's very good. Yeah, we have to be careful what we say. We have to be careful exactly how we say it. It's very good. Yes, very good. Good numbers. Well done, Glory. So the answer, it is cryolite. Well done, Shama. It is cryolite. The answer is this. It is called cryolite, and this is what you should say. The mixture of aluminium oxide and cryolite melts at a much lower temperature than pure aluminium oxide. So you shouldn't say it is just there to lower the temperature or to lower the melting temperature of aluminium oxide, because it does not lower the melting temperature of aluminium oxide. The mixture melts at a lower temperature. Okay, the mixture melts at a lower temperature. Okay, well, that is the end of today's chemistry. I'm sorry it's not mathematics, but it isn't. It wasn't mathematics. That is the end of today's session. I hope it was useful. What we are going to do next time, bye-bye Kabiro, thank you very much for being here. What we're going to do next time is we will look at some more examples of electrolysis and reduction. We will look at specific metals, we will look at their uses, and we will then go on to their physical and chemical properties. We will do it the same as this, so we will have some teaching and then some questions. And then in the third week, we will finish with the pollution and so on, and then we will have some real KCSE questions to look at and to be able to do, which are quite hard. I'm just going to stop recording now